Okay, sir. Shall we start?
Please, whenever you say.
Okay. Okay, good evening, everybody. Welcome once again to this 1 week FTP on environmental audit, a tool for sustainable industrialization. Today we have with us Dr. R.A. Christian, sir. Sir had completed his BE Civil in 1985 from BVM College, ME in Civil Engineering in environment from in the year 1988 from SVR, PhD in 2001 from SVR. Sir had joined the civil engineering department of SVR in the year 1987 and served the institute for 38 long years at various positions like Dean PND, Dean Faculty and Student Welfare, in charge training and placement, and ultimately voluntarily retired as a professor and head of civil engineering department recently on 31st January 2025. Sir has served as a member of Board of Governance at SVNIT along with his membership in various prestigious organizations. 15 students have acquired the PhD degree under his guideship. Sir has published 100 research papers in reputed journals and co-authored a book entitled Wastewater Treatment Concepts and Design Approach. We are very lucky to have you, sir, here in our session. Thank you for addressing the session, sir.
Okay. So, at the outset, good evening to you all. And let me first take this opportunity to thank all the organizers for giving me chance to uh, say something on air pollution control equipment. A very interesting topic for the faculty development program because Gujarat is one of the state which initiated environmental audit, and many of you who are in this FDP might be the members of the environmental audit team. And therefore, it is essential that you understand air pollution aspects and particularly the control technology which the industry uses for the stack emission control. So, from this angle, this particular presentation will be useful to you. Of course, those of you who have already acquired a master's degree in environmental engineering might be aware of the control technologies which are available, the equipment which are available, and which are put onto this stack. Uh, but for such participants, this could be a refresher type of presentation to just recollect what probably you studied at master's level. So let us go through with this understanding into the presentation with slide number 1. So air pollution control. When we talk of air pollution, uh, compared to the wastewater treatment and its disposal, air pollution control is technically difficult and it is expensive. If I compare air pollution control and wastewater treatment, you all are aware that in wastewater treatment, we are able to achieve uh, ZLD, that is zero level discharge. Industry can treat the wastewater and reuse it and can, prevent from making any discharges of wastewater. But technically speaking, in terms of the air pollution, that is not possible. In the sense that treating the air pollutants to the extent that there is no pollution at all in the plume that goes out of this stack, it is not only technically difficult, though it may be uh, viable to one extent. We may say that technically it is viable. It is very expensive. It is so expensive that we cannot achieve, as you can say, zero level emission in the from this tech. So in that regard, we are always disposing something, discharging something in the atmosphere in the form of emission. It can be gases, it can be particulate matter, and whatever goes out from this tech. And it is in the atmosphere, it remains in the atmosphere. And as we can see here, that rain is the only air cleaning mechanism which is available to us. Of course, it's available only on a particular season. So removal of pollutants which are released into the atmosphere, rain is the scavenging uh, natural resource which particularly uh, uses this water droplets to clean the air. And with these limitations, we can say that good air quality that we expect into the ambient atmosphere, it depends on, number one, pollution prevention, and number two, limiting what is emitted from this tech. So these are the two objectives that we should look into uh, the particular aspect when we talk of the ambient air quality: pollution prevention and limiting the uh, emissions. So from this angle, what are the control options that we have? Looking to the figure, uh, there are numbers 1 to 5. So we have one, which is the source which generates the air pollution. There is a mechanism which would collect the air pollution which is uh, emitted from the source. There it can go, because many times, the flue gas which is emitted from the source, it can be very hot. So the first aspect might be cooling it off, and then there might be treatment of the cooled air, flue gas, and finally it goes to this stack which is high enough to disperse the pollution into the atmosphere so as to minimize its impact in the ambient atmosphere. So this is the phenomena, or this is the uh, what you can say, the theory of how the air emissions are generated and finally goes out into the atmosphere and gets dispersed. So in this regard, if we look into the control of pollutants, as we saw, as I said earlier, the treatment is the most serious problem in the air pollution control. Recycling of the exhaust gases wherever possible is one of the means of control, recycling. But many stationary industries, they do recycle exhaust gases. Usually you can say carbon monoxide and volatile organic compounds as fuel for processes, and CO releases heat when burned to carbon dioxide. So such type of reuses and recycling of the exhaust gases has been tried wherever possible to minimize the gas going into the atmosphere. So the options has to be studied before we finalize and come to a conclusion of what control measures are particularly available. Now, before we switch on to the control, one must focus on the source. Source correction is one of the best options of preventing the generation of the pollutant itself in the flue gas. So that includes changing or eliminating a process, particularly in the manufacturing or whatever, which produces the pollutants which has to be discharged into the flue gas. So Of course, many times it is easier and than trying to trap the pollutants. So many attempts have been made in this direction also, that people have changed the process. People have changed uh, the process as a whole, change the equipment of manufacturing process, so that they try to avoid forming the pollutant itself at the source. So that is the first attempt that ever has to be made whenever we talk of the pollution control. A process or a product may be necessary, but could be changed to control the emissions. For example, the raw material itself could be changed so that the uh, pollution emission is itself controlled at source. Like, for example, it is given here that removal of sulfur from coal and oil before the fuel is burned, that reduces the amount of sulfur dioxide emitted. The type of the coal used, because the sulfur content varies from coal to coal. Different types of coal has different types of sulfur content. Of course, those are the source corrections that can be applied, but again, the economical aspect comes into picture, that low sulfur content coal might be expensive than the ordinary coal which has high sulfur content. So optionally, if we are very stringent, very strict to control the pollutants, then the source correction is the best way of doing it. Strictly speaking, such measures that we are talking about, as process change, or as I said, raw material substitution, and equipment modification, process equipment modification, these are the standard emission standards. These things are attempted to make the emission standards, and these are known as the control measures. So, vis-a-vis, if we talk about the abatement refers to all devices and methods which are employed to decrease the quantity of pollutant reaching the atmosphere once it has been generated by the source. So pollution control and abatement goes hand in hand, and the equipment which we are going to talk about, it tries to reduce the quantity of pollutants which are carried on into the flue gas, and before it slips into the atmosphere from this stack, we try to control and reduce that uh, pollutant. So that is abatement. So we are going to discuss in this particular presentation those methods which can be used. Say, for example, from the figure, if you recollect what we saw, the first thing was to take up the cooling part of it. The exhaust gases which are emitted from the source, the manufacturing process, whatever it may be, they are sometimes very hot. And before they can be taken to the control equipment, it is essential that such hot gases should be cooled first. Then only it can be taken up for further treatment in the treatment equipment or the control equipment. So the cooling of these gases, it drops the, it may also sometimes drop the temperature of the gas below the condensation point, and at that point of time some of the air pollutants may be condensed and get converted into the liquid form due to the cooling of the flue gas, and that itself converts the air pollution problem to the liquid pollution problem, and these liquids are required to be treated before it can be disposed of. So air pollution in cooling sometimes gets converted to liquid pollution problem. The methods of cooling, if we talk about, we have the methods like dilution, we have the methods like quenching, and we have the methods like heat exchange, where the gases pass from uh, continuous coil and and the gases come in contact with water externally, where the coil is continuously cooled by the water, and the heat exchange takes place. So these are all cooling methods which are available. And talking of the quenching method has the added advantage that some of the gases itself also can be scrubbed out while quenching the heat out of the flue gas. And the particulate matter also sometimes can be uh, you know uh, taken out from the process of quenching, and of course that will yield the formation of a dirty liquid that requires itself to be treated before you can dispose it of. So this method, as it goes on to in the discussion, as we are saying and seeing, that it is a method which converts the air pollution problem to the wastewater treatment problem. Cooling coils, which I talked about, are probably the most widely used cooling method, and they are especially appropriate where the heat can be conserved. So this method of cooling is many times applied to cool down the gases and remove the pollutants before it goes into the atmosphere. There is another part of it that after cooling, the flue gas passes through the treatment aspect, where the selection of the correct treatment device has to be thought of, which matches the features of the characteristics of the pollutant which is to be treated. So when we are talking about the flue gas, which carries gases as well as particles, focusing on the particles may vary considerably in size over many orders of magnitude. And from the ideal gas molecules to macroscopic particles, several in diameters, are found to be there in the flue gas. So the treatment device or the control technology which is to be adopted has to consider all these aspects of the particle size variation while deciding upon what type of control device to the stack for the flue gas is to be selected. And therefore, as we see that considering the size variation in the particles, we can also conclude and say that one device will not be effective and efficient for all type of particle size and all type of pollutants. And therefore, looking to the size distribution, various devices will have to be selected, and also we will have to consider the chemical characteristics or the behavior of the pollutants or the particulate matter or the gas, so as to say, that may also affect the selection process of a control equipment. So the various air pollution control devices that we are talking about now, keeping these aspects in mind regarding the temperature, and then regarding the type of the size of the particulate matter, and regarding the chemical characteristics of the gases and the particles, we can say that we have to look into two different aspects of control devices. The first type of the control devices that we will focus more on into this presentation is the control of the particulate matter. There will be a limited discussion on the control of the gases pollutants, because depending upon the type of the gas that you are trying to trap or scrub out, there are different technologies and methods available. Of course, it all depends upon the scrubbing liquid that you have to use to scrub out the gases, but the control technology would be the same. So when we come to that point, I'll specify and tell you how the control of the gases pollutants uh, have to take place. But most of the presentation, as for this particular my presentation, will focus more on particulate matter. So particulate matter collection mechanisms when we talk of. This collection and removal of the particulates from the flue gas, it consists of four different steps which we have to first understand. Before we talk in detail about the control equipment, we have to first understand what are the forces or what are the four steps in which this removal uh, of the particulate matter happens. The first thing is understand about the external force that has to be applied, which will make the particles to develop a velocity such that it will be displaced and removed from the flue gas mainstream, and then it will be directed to a collection mechanism or the retrieval section area. So the first thing is to think about what are the forces available which can separate out the particles from the flue gas stream and displace it out of the gas flow and then direct it towards the collection system. That is the first thing. Second thing is the particle should be retained in that area where it is removed or taken up for retrieval with strong enough forces so that they are not re-entrained back into the mainstream. So whatever the particles are removed from the gas stream has to be retained there, and care should be taken to see that they are not re-entrained back so that they may escape into the stack with the flue gas. So this is the second important point that has to be thought of and considered. The third point is, or this third step is, that the removed particles are collected and recovered uh, uh, periodically or continuously, as the case may be, and then they are subsequently removed from the system. And thereafter the ultimate disposition of this particle, which takes place after the removal, which completes the complete process of air purification or removal of particles from uh, the flue gas stream. So these are the four important steps, and these steps, as we'll see and discuss the air pollution control equipment, you will be able to appreciate how this thing is achieved and what are the forces that are uh, employed externally to uh, displace the particles or remove the particles from the uh, flue gas. The forces that are basically considered as tools to remove the particles from the flue gas stream are six main forces which are used in pollution control, particle control equipment. The first one is a very simple gravity settling force, centrifugal action, inertial impaction and interception, electrostatic attraction, thermophiles and diffusophiles, and Brownian motion are the main uh, forces which are used in the collection mechanism. All of these forces are used, or one or two of the forces may be used, and uh, it all depends upon which particulate matter you are interested to separate out and collect. So the force that has to be used, it all depends upon the target particle size which is considered to be removed. So that's an important point here. Now, based on this, starting with, of course, the different uh, control mechanisms that we are going to study are in the order of the simplest to the most efficient ones as we go further discussing each and every one of these collection mechanisms. The simplest one that is used is the gravity settling chamber. And as the name itself suggests, you must be aware now that it uses gravity force, the force of gravity in the device to make the particles to settle. So the gravity settler, it was one of the first devices which was used to control the particulate emissions. It is a very simple device and a very simple concept on which the particulate removal takes place. Uh, it talks about, or it considers the gas velocity, which is in a way reduced. Say, for example, expanding uh, the pipe in which the gas is flowing, expanding it so that all of a sudden the expanded of the gas considerably, and thus the gas which is flowing, it loses its particle carrying capacity, and thus it allows the particle to get separated and settled out under the action of gravity. So here the mechanism is so simple that just the velocity control without any external power source or any other source used, because gravity is a simple natural resource which is available, and that is used here to simply control the velocity is controlled, so that the gas, flowing gas, loses its ability to carry the particle along with it, and then the particle settles under gravity. One of the primary features uh, of this device is that the external force which is causing the uh, separation is provided by the nature. So it is a natural resource. The gravitational force that we are using, it's a natural resource available free of cost. So the chambers used in the industry, however, there is a limitation which the industry uses this particular device, that particles of larger size only are removed. Smaller particles are not removed. Of course, particles of 40 to 60 in diameter are generally targeted to be separated out in gravity settling chambers. Theoretically speaking, if you give a very long gravity settling chamber, the finer particles also may settle. But as I said, there are technical, economical problems that such things may not and cannot be attempted, and therefore this technology of gravity settling chambers is used only for large particle removal, 40 to 60 diameter. Now, there are basically two types of uh, dry gravity settlers. The simple expansion chamber that we talked about and discussed so far. And the second one, which is a modification of this expansion chamber, is the multiple tray settling chamber. And that increases the efficiency of the simple expansion chamber, that we will see how it works in the uh, figure here. This figure is a simple horizontal flow settling chamber. So as you see here, particle laden gas is entering from one end. There is a small duct in which the flue gas enters. All of a sudden that experiences the expansion which is there in the chamber, and thereby because q is equal to area into velocity, so area increases, so velocity considerably drops. And in that regard, the heavier particles, as you see here, uh, the flue gas loses its capacity to carry these particles further out from the outlet, and the heavier particles, they are settling into what we call it as the dust collection hoppers, and from there periodically or continuously the particles which are settled and separated out can be removed from the gas stream, and then the cleaner gas, it moves out from the gas outlet, and then it may go to the further other devices to remove the smaller particles, or it may be directly be attached to the stack. The unit, as we saw, is a long horizontal box type with an inlet and an outlet, and also it has dust collection hoppers. And primarily, it depends upon a very simple, naturally available source of removal, that is gravity, which separates the particles from the main gas stream. So particle laden gas, as you recollect from the figure, it enters into the unit from gas inlet, and then there is a sudden expansion where the uh, gas and particles are separated out because of the reduction in the velocity which has happened, and all these settled out particles, removed particles, they are removed by the force of gravity. Reduced gas velocities in the range of zero point 0.3 to 3 meters per second, are they are falling into the dust hoppers. And as I said, theoretically, you may say that okay, we may provide a very long settling chamber, and that would remove even the smaller particles. Theoretically, yes, it's possible. Practically, that's not possible to have because of the site conditions which cannot provide such long chambers. So technically, it is not feasible to have this type of settling chambers. But as it says, up till now we have seen that 40 to 60 larger size particles are removed without any external force of electricity or any other uh, such uh, energy. Velocity must not be so high. That is, we are talking about again the velocity of the flue gas. It should not be so high that the settled particles are re-entrained, remounted into the flue gas. That care has to be taken. So that is the only concern, that the particles which are separated out may get re-entrained into the flue gas stream. Now, the physical description, we can have the concern in the design is the length, the width, the height, the number of shelves if applicable. That's the modification which I was talking about, and we'll see in the next slide that how these shelves may be useful to improve the efficiency of the settling chamber, and any other ancillary equipment like inlet, outlet, cleaning mechanisms, hoppers, etc. So this is a very simple type of simplest form of gravity settling chamber. And when we are using multiple tray in the settling chambers, we call it as the Howard settling chamber, and it is shown here. You can see here that the simple chamber, which was there earlier, expanded chamber, has multiple trays. So it reduces the uh, settlement distance of the particles, and thereby increases the efficiency of the uh, gas cleaning mechanism, which can be achieved by the Howard settling multiple tray type of gravity settling chamber. So again, the particle laden gas enters here, passes through over the multiple layered tray, and then cleaner gas goes out of the system. Now, n number of plates can be introduced, horizontal plates, to shorten the settling path and to improve the collection efficiency. And in this regard, the particles as small as 15 micrometer in diameter can be separated. Each shelf of tray or the unit can collect dust by again simple gravitational mechanism, and because the distance has been considerably reduced, overall efficiency it is increased compared to the simple gravity settling chambers. Can be of great can uh, so overall efficiency of the Howard settling chamber can be greater than the horizontal simple chamber. So that's the modification which one can have and can suggest to the industry for higher efficiency of this particle collection mechanism through gravity. And also another way of making the system more efficient is to provide the baffles, and these baffles make the gas to flow by turning its direction. So one must understand here that when the gas direction is changed, the particles, because they are heavier than the gas, will not be able to travel with the flow direction. And at that point, the particles will be separated out and removed from the gas stream. So this is another way of improving the efficiency of the uh, gravity settling chamber using a baffle chamber. So cleaner air goes out from one end and the dirty air enters for cleaning in the gravity chamber. This is again the same type of a system where target plates are used to achieve better flow, or to give better detention into this chamber for the gas. Otherwise the gas would simply flow out within the shortest time. So this targeted airflow direction also can separate out more particles, heavy particles, which are dropping out, and then the smaller particles escape from the settling chamber. A little bit higher version of the control device that we have is known as cyclones. The cyclones again are cost effective in the sense that they do not use any uh, electricity, or power is not consumed. A simple mechanism is used here. It's a relatively low cost method which removes particles from the gas stream. However, designing of the cyclones is much more complicated compared to the gravity settling chambers. But efficiency wise, we can say that cyclones perform much better than the gravity settling chambers. So let's see how the cyclones work. Of course, there are better systems compared to cyclones, that is the electrostatic precipitator and the baghouse and the venturi scrubbers. But many times this cyclones, they are used as pre-cleaners before the particle laden gas enters into the efficient systems like ESPs or baghouse or venturi scrubbers. So it's a low cost method and may be used as a precursor. So there is a combination of the cyclone followed by ESP or a baghouse filter, which gives more effective uh, performance and reduces the particle load on ESP or baghouse filters. Cyclones, they are in many size, they can be made in many size and shape, and they do not have any moving part. From small cyclones like 1 to 2 centimeter to very large cyclones like 5-meter diameter cyclones can be used after the wet scrubbers, and the basic separation principle, however the smaller or the larger cyclones would remain the same. This is the figure which explains how the particles move in the cyclone. So the design of the cyclone should be such, it's a cylindrical or a circular shape in cross section, and the inlet essentially has to be tangential to the body of the cyclone. So this is the body of the cyclone, and this is the inlet where the particle laden gas enters into the cyclone. It's a tubular structure, you can say, with the cross section showing you the movement of the gas as the particle laden gas enters into the cyclone. So it strikes the cyclone wall, and the air takes a helical turn, and in that as I said earlier, that whenever the air turns its direction, basically the particles, the heavier particles, because of the inertia, are not able to keep pace with the movement of the air, and therefore they are not carried along with the flow of the air. So larger particles, they move towards the cyclone wall, and they are separated out, and the gas stream actually in that time separates the particles from the flue gas. And depending upon the design of the cyclone and the length of the cyclone, the number of times this helical movement of the gas takes place, it depends upon the design and the uh, length of the cyclone. So it's very much like a funnel of a tornado. You must have seen a tornado. Western countries uh, faces a lot of tornado issues and problems. So there is a turning movement of air where the dust is frequently turning in the helical form. So this repeated turning provides the particles opportunities to separate out from the gas stream. So we would like to have more and more number of turnings to increase the efficiency of the cyclone. So that's the concept. And this figure itself also shows here that the range of particles size is uh, it depends upon the design, the overall diameter of the cyclone, and the length of the uh, cyclone body. So flue gas enters into the cyclone tangentially, as I said, and the flue gas, once it strikes the circular body of the cyclone, it moves around in the helical form, going down, separating the particles here, as the particles do not are not in a position because of inertia to move with the uh, flue gas, and then they are dropped out from the gas stream, and they are collected in the hopper bottom, and the flue gas, the clean gas, it goes out from the cyclone. So this is a typical tangential entry cyclone which is normally used in many of the industries. You might see those type of structures and the control mechanisms. Another type of cyclone which is used is known as the axial entry cyclone. So here you don't see any tangential entry of the uh, flue gas, but it enters uh, from here, and dirty gas enters through this opening, and there are these rotary veins which gives the spiral helical movement to the air. That is very essential, that unless and until this helical spiral movement of the air takes place, the flue gas takes place, the particles cannot be separated. So these veins which are there at the bottom, sorry, at the top, they direct the gas, flue gas stream, giving it helical movement, and gases enters from the top. Because of the helical movement, the particles are separated, the vortex is created, and the clean gas separator tube carries out the clean gas from the cyclone. So this is another way the cyclone can be designed. And this type of axial entry cyclone, it is commonly used in multi-cyclone configuration, and that multi-cyclone configuration, so small cyclones, many in number, will provide higher efficiency. We'll see that uh, at a later point in the presentation. So these cyclones, they have four major parts which are seen in the figure: the inlet, the cyclone body, the dust discharge system or the separator, the hopper bottom, and then finally the air outlet. All this are to be designed in a way to increase the efficiency. So the gas is directed by the inlet, which is instrumental in formation of the vortex. Either it may be tangential or it may be axial, as we saw in two different types of cyclones. Then the helical movement gas flow, because of the vortex formed by the inlet, it enters into the cyclone body, and thereby, depending upon the length of the cyclone body, the number of vortices can be created, which particularly uh, you know forces the particulate matter to the wall, and then thereby separates the particulate matter from the flue gas, and then it slides down the cyclone body into the cone, and uh, the particles are finally collected at the bottom of the cone into the hopper bottom. And very important that velocity of the gas must be maintained, and the helical motion of the gas also should be maintained. So gas changes its direction from downward to upward, passes from the opening in the upward direction, and uh, it passes through the vortex finder, the tube which we saw earlier. This tube is the vortex finder, and that vortex finder takes the cleaner air out of the cyclone, and the particulate matter drops into the hopper bottom, where it is periodically or continuously removed. So this is a very simple mechanism of separating the particles, effective compared to the gravity settling chambers. Removal efficiency for a given size of particle, it depends upon the cyclone dimensions. The efficiency of the cyclone at a given flow rate, it is affected by its diameter, the overall length, and the number of tons. So in the design of a cyclone, it's important to control and design effectively the diameter of the cyclone, the length of the body of the cyclone, and the number of turns of the vortex that can be created. Because more the number of turns of the vortex, uh, better is the removal efficiency. Now, to increase the velocity, smaller inlet to the cyclone may be preferred. But again, this smaller inlet would result into a greater velocity. However, it would also result into a larger pressure drop. So these are the limitations and some considerations which have to be thought of when we look into the design of the cyclones. Small cyclones are more effective. However, the small cyclones will have a higher pressure drop and are limited to smaller flow rates, volumetric flow rates. Small cyclones, basically they are used in multi-cyclone type of arrangement, and uh, they are arranged in either series or in parallel, and it increases the efficiency at the lower pressure drops. So that is the advantage of using the smaller cyclones. However, by doing so, we are increasing the cost of installation. We are increasing the cost of maintenance. So that is the uh, disadvantage, that multi-cyclone, though more effective, can prove to be expensive both in installation and maintenance. So they get plugged also more easily, and therefore it would demand larger and frequent maintenance issues. So that is the aspect we have to look into. Hoppers, when they are used, they can lead into the re-entrainment of the particulate matter into the flue gas. So that's also another drawback. Smaller cyclone tube, which we'll see in the uh, figure next slide, uh, the vein in the inlet to that type of smaller cyclone will be like the axial inlet, which passes through the veins, which create the spinning movement into the gas stream. And most commercial tubes of 6, 9, or 12 inches in diameter are used in the uh, small diameter multiple cyclone. Limited gas handling capacity it has because of the lower volumetric flow. Large number of tubes in parallel are to be installed in a simple or single collector. A small diameter creates more rapid spinning, and therefore it gives greater efficiency compared to the large diameter cyclones. And the particles moving outward in the spinning gas stream have relatively shorter distance to travel because these are small cyclones. So the body of cyclone itself is small. So the particles have to travel a shorter distance before they can be separated out and drop out into the collection hopper. So these features which we have discussed here, they allow small diameter multiple cyclones to collect considerably smaller particles, and they are capable of removing particles diameter down to 5 micrometers. So that's the advantage of using these smaller particles. As we can see here, this is a small cyclone tube, and as I said, the guiding vanes which are there, the entry of the gas is from the top, we can see here. So this inlet spinner vane, it gives a spiral motion to the air flue gas entering into the small body of the cyclone, where the dirty gas flows in, takes the helical turns, separates the particles, and goes to the hopper bottom. So this is the container where multiple cyclones are installed like this, and this is the outlet where it goes and gets collected into the hopper bottom at the bottom of the system, where it is continuously or periodically, removed. This mechanism. Uh, uh, Diagram which explains hot flue gas which comes here. It is passing through the condenser tube, so heat exchange takes place here. So this condenser tube which we talked about earlier, that heat, the hot air has to be cooled down first before it can be passed to the multicyclone mechanism, and a draft forced draft induced draft fan is used to create a draft for the air to be sucked, and it goes and passes into the multicyclone, and from the top it goes again, induced draft fan is used so that the clean air flows out, and this is where the dust hopper collects the dust. So this is the mechanism of multicyclone arrangement. This figure you can get from the internet. These are the various sizes of H1, H2, D1, DE, DE, S, inlet, outlet. So these are the design concepts which are given on the internet. You can get it for designing a cyclone for the aspects which we have seen earlier for the removal. The important is the inlet, tangential flow inlet, the body of the cyclone, and the collection mechanism, so that the particles do not get re-entrained. So this figure also explains that aspect which we discussed so far. This is the figure which shows a diagram which shows figure which shows how the cyclones would look if you visit any of the industry while doing the audit. You can see this cyclone body is there. These are the hopper bottoms, uh, the uh, the the tangential inlet to the uh, body of the cyclone. Here also the tangential inlet is seen, and then the outlet, this outlet takes out the clean air. So this very clearly explains. Now once next time when you visit the cyclone, you can keep these things in mind to see how the cyclone operates. Another better control equipment, is the electrostatic precipitator. It's one of the best, you can say, and unique among the gas cleaning equipment. Many of the industries use this electrostatic precipitators, uh, uh, in which the force separates particles from the gas stream are applied directly to the particles themselves, and energy is required. So it is energy hungry system. So it's always expensive to use and operate ESPs because it requires energy for the effective separation of the particles from the flue gas. And therefore, uh, the separation is more effective because of the electric current which is used. The fundamental advantage that we see that smaller particles also are removed by using ESP. That's why and meeting the uh, emission norms, flue gas stack emission norms. So it has resulted in widespread use in the industries where large gas volumes with higher efficiencies are required to be collected and removed before the gas is finally released from the stack. It consists of three fundamental steps of removal. The first is the particle is charging, particle collection, and the removal of the collected dust. These are the three steps. So particle charging, it happens because of a mechanism which creates what is known as a corona. And corona is a electrically charged field which produces ions, charged ions, and these charged ions become attached to the particles, giving some sort of a charge to the particles, which are then attracted to the opposite charged attraction plates, disposal plates. And this corona requires high non-uniform electric field. That is where the power is consumed, and that therefore this is a cost operating mechanism where electric field is to be created to generate a corona. And this condition occurs, the formation of the corona occurs when the high voltage of electricity is applied between the wires and the collection electrodes. So the wires are having some charge, electrodes are having some charge, and because of these charges across the wire in the field, some corona high charged layer of uh, ions are formed. And these ions produced, they move towards the collection electrodes, carrying along with them the particles which are attached to it. They collide with the electrodes and then they slide down into the hopper bottoms. And that is how the particles are removed uh, through the charged ions. So you can see here, this is the cross section, partial cut cross section of the electrostatic precipitator. The dirty flue gas enters from here. These are the collection plates or charge collection electrodes plates which are there. And in between them, you can see here these black lines. They represent the charged wires, which creates the corona. The next figure will see that. So in that case, the particles enter here. They are passing through the corona field in between the uh, plates, and the particles, they get charged, set out from the separate out by collection from the uh, electrodes, discharge electrodes, and then the cleaner air passes out from the other end of the electrostatic precipitator. This is how the discharge electrodes are there, the collection electrodes are there, the discharge electrodes are, this is the cross section. So vertical wires which are suspended in between the collection electrodes, and the differential charge between this electrodes and the collection and the discharge electrodes creates what is known as the ionizing field or the corona, and the particles which are passing through the corona get charged and gets attracted to the collection electrodes, fall out into the hopper bottom, and are removed from the flue gas. So particle laden gas enters from one side and the clean gas goes out from the other. So this is another cross section which explains very clearly how the particle-laden flue gas would be entering, passing through the number of electrodes, particles get separate out, high voltage power supply mechanism is at the top, the discharge electrodes would be there suspended as wires, and then at the bottom you have the hoppers which collects the particles, and finally the clean gas is removed out from the uh, uh, outlet, and then it can go to the uh, stack. So this is the conceptual working mechanism of electrostatic precipitators. Now, electrostatic precipitators may be applied in series in field so as to improve the efficiency of its working. So there can be a typical 2 to 8 chambers. These are the fields, electric fields. This two light and dark green, they are in parallel, and from here to here, from field 1 to field 4, from inlet to outlet, this is in series. So making more and more particles to be charged and removed, thereby improving the efficiency of the uh, electrostatic precipitator. So this type of arrangement also is possible in the ESP. Uh, but again, you have to consider here the aspect that these are all, expensive method. This is an expensive method as it consumes power and electricity. This is a mechanism. You can see whenever you go for your next audit, you can see how the electrostatic precipitator would look like. These are two different pictures, and from here you can say that the dirty flue gas enters this chamber. This house would contain the discharge and the collecting electrodes. You can very easily see the hopper bottoms, and then the outlet from where the clean air comes out and goes to the stack. So this is the mechanism of how the electrostatic precipitator would look. But it is better that you study and digest what actually happens inside, because once we go to the industry, this is what we see, and we don't have any idea of how the system works unless and until you have studied air pollution as a subject in your master's or BTech course. The advantages that we have of the ESPs are that they can have very high efficiencies because strong electric forces are applied, and even smaller particles can be, separated out. And the thing can be used only when the gas stream is not explosive and it does not contain entrained droplets or sticky material. Otherwise, that would remove or reduce the efficiency of uh, the ESPs over the period of time. The composition of the particulate matter also has to be very important because electric conductivity of the particle is also important. The resistivity of the particle to conduct electricity is very important because the resistivity of the particle to conduct electricity would influence upon the removal efficiency and will reduce the uh, you know the particle removal efficiency. So that has to be seen that what type of particle you are dealing with, and as the resistivity increases, the particle ability to conduct the electricity decreases, and thereby uh, the efficiency reduces. So when the resistivity is moderate range of 10 raised to the power 8 to 10 raised to the power 10 ohm centimeter, it is to be used. So that's the limitation of the disadvantage of the ESP, that what type of particle you are working with. Then another good system is the baghouse filter. This is the oldest and the simplest form of the most efficient uh, method of control of particle removal from the gas stream. It is a simple filter mechanism through a fabric filter. So air is allowed to pass through a fabric media, which uh, prevents the particles to pass through it and allows the air to pass through it. So they are capable of providing high collection efficiency because of this filtering media. So as small as zero point 0.1 micrometer particles are removed, and subsequent quantity, as more and more particles get trapped, again the particle size removal may go to be as small as 0.01 micrometer. So in a simple form, the fabric filter consists of woven felted fabric, just like a cloth, and combination of factors would affect the particle filtration. Woven fabrics would create the dust cake. So when more and more particles get settled onto the fabric, the dust cake created also further helps in the sieving mechanism. However, a time may come where the pressure drop may increase to an extent that the fabric will have to be cleaned. So the thickness of the dust cake formed may increase the pressure drop and decrease the airflow movement, and at that time the filters are required to be uh, cleaned at the predetermined interval. And dust cleaning is done by the gravity or mechanical means, uh, by shaking uh, the tubes which carry the uh, fabric filter. So if we see here, this is the fabric filter bag which is housed into the, see again when we go to the industry we just see this type of the, this is a bag house filter where number of such bags, maybe hundreds or thousands of such bags would be suspended, and the air would be made to flow either in or out, passing through the uh, fabric. So the bags are hanging in the bag house. A number of bags, maybe less than a dozen to 1,000 of such bags would be suspended, and maybe the inside of the bag house would be compartmentalized to give the uniform flow, and the air may be allowed to pass from inside to outside or from outside to inside of the filtering cloth. So the basic filtering process which is happening here, just passing through the filters, and the method of removal and collection will vary on the type of filter or the fabric, the cleaning mechanism, the equipment geometry, and the mode of operation. So depending upon the factors, as I said, the flow process, uh, there can be bottom feed or the top feed bag house filters. Top feed bag house filters allow the air to pass from the top. It can be from inside to the outside, or it can be from the outside to the inside. So there are different methods and different flow processes which can be, employed to uh, clean the gas passing through the baghouse filter. The cleaning normally is done by reversing the flow process so that the cake which is formed may be dislodged and falls into the hopper bottom. And as I said that it is necessary to clean because it will be the dust cake will develop the differential pressure and has to be cleaned periodically. So this is what the bottom feed into out. This is the bag filter. This is the top feed into out, and this is the bottom feed out to in. So you can have a different combination of the airflow mechanism so far as the bag house filters are concerned. Uh, these filters have the option that they can be either operated on continuous or intermittent operation. So depending upon the way the operational schedule of the uh, dust source is there, you can have the intermittent or continuous operation mechanism, and the intermittent operation system can have gas cleaning function, and the filter cleaning function also can be employed. Reverse type fabric filter uh, can be used for large industry for particle laden gas entering from the bottom from inside to outside. That is all what we have discussed. So number of such combinations are to be used. And when cleaning this type of filters, it is necessary that dampers are used to isolate the compartments of bags. To have a continuous operation, one compartment can be stopped, the other compartment can be kept in operation, so that the continuous operation can be carried out. So dampers are used to separate the isolation of the compartments, and then the flow gas flow also can be diverged into the other direction, and the dust cake can be removed. So this is how the compartmentalization of the flue gas may happen, where the uh, cleaning mechanism can take place. So reverse flow, these are the bags into the baghouse filter. So ID fan is applied so that the clean air is sucked out and passes through the stack. This is another type of cleaning mechanism which has a pulse jet. So this type of cleaning mechanism induces compressed air pulse jet inside the uh, bag, so that the pulse can dislodge the or remove the dust cake which is actually accumulated either in the inside or outside, and then very salt pulses can be given of the compressed air system, and that would remove the cakes which are formed in the bag house, and then uh, it can be cleaned. So that's the cleaning mechanism for a bag house filter. Advantages and disadvantages of this filter are that they have very high efficiency, collection efficiency, when 99 to 99.5% of collection efficiency is required. This type of baghouse filters can be considered. Of course, it depends upon the characteristics of the particulate matter and the design of the fabric filter which is selected. And they are very efficient at collecting the entire size range of the uh, particles which we talk about. The performance is usually depend upon the chemical composition. However, the particulate matter uh, that should not be any corrosive type of particulate matter, or the flue gas should not be corrosive to the fabric which is used. The flow of the flue gas should not chemically attack the filter media, otherwise this would reduce the life of the uh, filter bags which are used, and they would need to be replaced. Of course, there is a need of replacing the worn out filter bags, so that maintenance also has to be considered when thinking about the bag house filter as a mechanism. uh, they are also not used, like disadvantages, when the flue gas is sticky or wet particles are there, then the filter bags may get clogged up easily. These materials will accumulate on the filter surface media and block the movement of air. So that is another disadvantage, and it should not be used in such case. However, it should also be very carefully designed, and potentially if there are combustible of or explosive particles or gas or vapors, then also it is very risky to use this type of fabric filters. So in such cases, when you have such a material to be cleaned from the flue gas, then alternative control techniques has to be uh, thought of, like using wet scrubbers, which are effective in that condition. So venturi scrubbers are another mechanism, or wet scrubbers, they are another mechanism which would use certain type of uh, liquid which is sprinkled over the polluted gas, and these water sprays would trap the particles which are passing into the flue gas, and then they are removed, attached to the particles, and then they move out with the liquid. So ultimately here the removal efficiency also is good, but we can say that this is converting the air pollution problem to the water pollution problem, and the water which goes out as the wastewater has to be cleaned and treated before it can be disposed of. So each of these techniques can effectively remove particulate matter, and venturi scrubbers can effectively remove even the gases from the gas streams like HCl or sulfur dioxide. So if you have a good type of the scrubbing media which would react and remove HCl and sulfur dioxide, when gases can be cleaned in this type of uh, mechanism. So they are more versatile in design and have higher efficiencies. And however, because they are having scrubbing liquid, it requires higher operating cost, and the byproducts are difficult to recover. And there is a problem, as I said, of transferring the air pollution to the water pollution, and the treatment of the wastewater is to be thought of. So in cost terms, venturi scrubbers are generally more expensive compared to the simple gravity settling chambers and cyclones, but they are less expensive compared to the high efficiency electrostatic precipitators and the backhouse. So it has a dual advantage that gases also can be scrubbed out. uh, Variety of wet scrubbers are available, and therefore the evaluation of the selection of the appropriate scrubber has to be considerably thought of, because it would require the spray mechanism to operate the scrubbers. This means that independent of the design, more power put into the system, greater will be the efficiency. However, we can say that it would become expensive to achieve greater efficiencies. These are the points to be considered while designing this system. So this is a simple system which shows dirty gas flowing in, and it can remove droplets ranging from 50 to 500 micrometer mm are produced here. They are sprinkled into this chamber, and these droplets are carried forward into the separation chamber, where from here it would collect the dust and trapped into the drops, and then the droplets are separated out, and the clean gas flows out. So this is a simple mechanism of a wet scrubber. This is again a diagram and a figure. So venturi scrubber, this is the scrubber mechanism where the particle laden gas may be cleaned here through the scrubber, and thereby thereafter it can be passed through the cyclonic separator, passing through the uh, discharge stack. So this is how the uh, different types of scrubber and cyclone combination can be used in a, mechanism uh, for cleaning of the gas stream. Spray towers, these are also like because of the shortage of time, I will be going fast. So liquid droplets are atomized into the spray nozzles, and bulk liquid is converted into liquid droplets, finely divided liquid droplets, which is the particle laden gas is forced to pass through between these droplets, where the particles are trapped into the droplets, and terminal velocity of the droplet is controlled typically from zero point 0.3 to 1.5, and mist eliminator for the greater velocities has to be uh, you know uh, provided, so that these droplets of water or the liquid should not escape from this stack into the ambient atmosphere. So mist eliminator has to be employed for higher velocities. So this is how the spray towers are used. This is vertical type of spray towers, the uh, liquid spraying mechanism. Now, depending upon either only particle is to be removed or some sort of gas also is to be scrubbed out, you can have the different types of liquid spray depending upon the gas. This is the horizontal cross type spray towers. This is again uh, uh, packed bed spray towers, which are also sometimes used in the industry. So this is all about the spray towers. This is how the spray tower would look if you visit any industry. But this is again the effective method of removing not only the particles but also the gaseous pollutants when appropriate spraying liquid is used. So this is all about the control equipment that are used in the uh, you can say industries. Now what I have not covered is the gaseous pollutant control. But as I said, depending upon the type of gas to be scrubbed, a spray tower can be used with appropriate scrubbing liquid so that the desired gas can be removed from the flue gas. Thank you so very much for listening to me patiently.
Thank you, sir. Thank you, sir, for this informative session. I would like to ask the participants if you have any query, then you may please put up your query to Christian, sir. Arvind Pachani, sir. Dr. Gaurav Agrawal.
Good day, sir.
Good day.
Sir, actually, regarding stack mounting, like if there is industry are old, so there is two problem can be like one is the 82D concept, okay,
Hmm.
regarding
Hmm.
the position of the sampling port.
Hmm.
Second, the size of the sampling old. Some of the industry are old more than 1980 or something. That's why their sampling port are not up to the mark. We can say more than less than 3 inch or something. So what we will do in that case?
See, there is no other option. That's a very genuine problem that I have seen many auditors do face that he there is only one way to do it, that you have to make the industry to compulsorily change the port where it is located with 82D concept and the requisite diameter of the sampling port. There is no other option that such text can be sampled. So it is your responsibility as an auditor to compel them to make the necessary changes. Otherwise, you can say that we are going to report to the pollution control board that you are not complying to the standards, because these are the mandatory requirements. Unless and until they are not there, you cannot monitor this tech. That's
Okay,
as
sir.
easy as that. Ah.
Okay, sir.
So you compel them. You say that it's a mandatory requirement. If you are not complying, I am putting in my adverse remarks. That's it.
Okay, sir.
Hmm.
Yes, Abhay Nagle,
Sir, there
sir.
is any sir, there is any
Okay.
CPCB guideline regarding the sampling port?
Of course, you can see the CPCB stempling, stack monitoring type of code which is there online available. You can see that in which the 8D 2D concept is also there, and the size of the the port size which is to be provided, that is also given. Everything is given in the CPCB manual for conducting this stack monitoring. You can refer to that.
No, no, sir. I'm not talking about the 8D 2D concept. I know that they have no, regarding the sampling port or sampling size can be changed
That
according to the industry.
why according to industry it has to be changed? It is standard. It is standard that
Okay,
there
sir.
is no variation in the sampling port so far as the industry to industry is concerned. Only
Okay, sir.
parameters to be considered for large and small stack is the traversing which has to be done. Otherwise, the sampling port, either another important point which comes out of this the discussion is how many sampling ports you should have. That depends upon the diameter of
Meter.
the stack, correct? So
Right.
either diagonally or two, three, four stacks, either rectangular or circular. So those norms are to be followed. Yes,
Okay, sir. Can I ask my question, sir?
Yes,
please.
please.
Hello.
Yeah, thank you very much, sir. A very condensed and very precise and very informative presentation. I'm really happy with that. Thanks a lot, sir. I
Thank you,
have one
Mr.
or two
Rafi.
questions, sir. Point number one, I mean, what I have found is that back filter versus ESP. Now, actually, people consider that ESP is more costly and all these things. If you do
Mm,
the power calculations, because back filter gives you a pressure drop of about 150 millimeters of water column,
mm,
whereas the pressure drop in an ESP is very negligible. It's less than 50.
mm.
So, under the circumstances, I feel that overall, back filter is costlier than ESP. Can I have your comments on that, sir?
Mm, Actually, you calculate those things, then it comes out to be that. But again, operating cost, maintenance cost, everything has to be looked into. Of course, both has its own pros and cons. Correct. Many industries go for the old industries. They go for the back filters. Many industries have gone for the ESPs. So it's all depending upon the industries. However, the power consumption, the rate of electricity power, uh, uh, rates increasing, all those things are there. So your point is very genuine, and it depends upon the industry to consider, because even the bags are to be replaced periodically
Yeah,
over the year.
exactly.
Yeah,
So if you
so
consider, yeah, now over 2 years, you need to replace the bags.
you need to
So,
replace the bags.
yeah, yeah. And you need compressed air also. I mean, consumption
Yes,
of compressed
yes,
air for
yes,
pulsing,
yes. That is for
then the
pulsing and all
replacement
is
of
there.
bags, and then, so overall, I feel ESP is a better solution than back
Comparatively,
filters.
yes, comparatively in efficiency wise also ESP are much better
Yes, yes, sir.
so far as the maintenance and all is concerned. Yeah.
Right, sir. One more small question, sir. Why is the inlet to cyclone always rectangular? I have not found any circular entry.
Uh, you see, probably it would be my way of thinking is that it would be a better tangential, movement.
But it is
If you
tangential
no,
inside.
tangentially,
Inside it is
because
tangential.
so a straight line, because if you take a circle, circular shape of the inlet, you may not get that face of tangential entry.
Got
Circle
it, sir.
may
Got it, sir. It has to, yeah, yeah,
yeah,
yeah, yeah.
to give a,
It
a,
has to
a
go through the cyclone
yes,
outlet in a
yes,
very
yes,
nice fashion. I mean, if it is
yes,
circular,
yes.
it cannot
So
reach because,
rectangular can give a better inlet than
yeah, yeah,
circular. That's the
yeah.
reason.
Because the inlet outlet is a vertical pipe. So
Yes,
to
that
move
can be
around that pipe,
considered
you cannot have
uh,
circular. You have to go for rectangular.
for
Got it,
rectangular.
sir.
Yes. Yeah.
Yes, yes.
Thank you.
Hello, sir.
Arvind
Sir, may I
Pachan.
Thanks, sir.
ask a
Hello.
question? Sir, may I ask question?
Please.
Uh, Sir, ESP, the capacity of the ESP, on which base it is decided? Like a field, one field, two field, three field, like that?
Uh, I'm sorry, like I have not done the design, so I would not attempt to answer that because I am not very sure. But as we saw in the presentation, the chambers 1, 2, 3, 4 field, which one of the slides showed. So I can say that whatever you are saying is correct. It all depends upon how many fields of electric chambers are given
Right,
before the flow goes out. So the design has to be that, because the inlet to each of these chambers would have a different particle size entering into it. So accordingly, that and if you recollect, the inlet nearer the very first chamber was dark, then lighter, lighter, lighter. So air was getting cleaner and cleaner and cleaner as you go from chamber 1 to chamber 4. So those design aspect will have to be considered.
Sir, is
Very
it required to design the number of fields required for particular efficiency level,
Hey,
or in most ES?
uh, as I said, I have not done the design of
Okay,
that,
okay, okay,
so
sir.
I
And
cannot,
sir,
and I would not like to answer that.
okay, sir, okay. And
I
sir,
would not.
how to measure the performance of the ESP?
Performance would be just easy. Like, see, depending upon performance can be measured by the total particle inlet and outlet, and to be more precise, particle size separation, and then what level of particles are removed. So the performance of this control equipment can be measured as a total efficiency and size wise efficiency removal of the particles can be considered if you have the facility and mechanism to do that, then that is how it
Okay.
can be done. Otherwise, total inlet and outlet difference of particles can be considered. Yeah.
Thank you, sir.
Okay, Arvind
Hello.
Pachani, sir. Just a
Hello,
moment.
sir.
Just a moment. Let us go in queue wise. Arvind Pachani, sir, do you have any question? You raised your hand 3 times. That's why. If not, then we shall proceed with Dr. Gaurav. Yes, Dr.
Hello.
Gaurav. Okay, yes, please. Arvind.
Hello.
I have already asked actually.
Yeah,
Hello,
Dr.
sir. My
Gaurav has.
question, my question is, how can we decide the number of bags with reference to capacity of the boiler? Means, if the capacity of boiler is 3 ton, then any specific criteria that this type of bags, the number of bags are required?
Again, my limitation is there. I would not answer this because, see, I have not done. But there is
It's a
a book,
design.
there is a book which I would recommend, Air Pollution Control. David Cooper is there. So
Okay.
he has given all the design of the different uh, control equipment. I'm sorry, I'm not able to satisfy your query because I have not entered into the design aspect.
Because
But
how can
there
we
are
decide that the provided bag is optimum or not?
But that is a part of the design.
that is the part of the design, and just as Yogesh sir said that you have to refer to the design manuals for that, and accordingly you have to do the selection. You have to look into
Okay.
that.
Okay.
Uh,
Okay. Thank you, sir.
Okay.
Okay, next question, please.
Hello,
Yeah.
sir. Good evening.
Good evening.
Sir, I have about the
Hello.
Your,
hello.
your voice is not audible.
Okay. Hello.
Yes, sir. You can hear me,
Yeah. Please.
sir. I have a question about stack monitoring. Company using the LPG gas, and they have come out the SO2 concentration is higher about the limit. So, which solution about for the control of the SO2 level?
See, control of SO2 is again by scrubbing out the gas.
Yeah.
But natural gas they are using,
Yeah, sir.
and they are getting SO2 problem.
Yeah, SO2 problem they have in stack mon out of the gas from the chimney.
And the consent allows them to use natural gas.
Yeah. They have a get the consent. They were approved from the GPCB.
Mhm. And my question is, if the consent, you have seen that SO2 is found in this flue gas,
Yes, sir.
does the consent, so what is the limit of that? Then they should get the quality of gas checked
Okay.
because the source is from there, or they are using some alternative mixture somewhere. You must check those things out, because the consent very clearly specifies if it's a natural gas, what are the emissions levels, that is already written there. You should check
Okay.
those things out. And the source of the natural gas.
Okay, sir.
Okay.
Maybe dry scrubbing is one of the
That's
solution.
the one. See, the
Dry
removal of sulfur
scrubbing.
dioxide is scrubbing with uh, lime and all that.
Hmm.
Yeah.
Okay, sir. Thank you.
Okay.
The next question, please.
Hello, hello, sir.
Yes.
Good
Yes.
good evening, sir. First of all, I want to thank for sharing such informative insights regarding the air pollution control devices. My
Thank
question
you.
is that, sir, in bag house cleaning system, there is a one method called sonic horn, in which we
Mm.
use low frequency sound waves to dislodge particles from the surface of the bag filter.
Mm.
So I want to know in which circumstances this method is used and is it more efficient?
Industry uses as per their need. I have not come across, this is sorry, I have not come across in literature that sonic wave pulses are used. But if they are used, then depending upon, as I said, these are pulse waves are already seen everywhere in the atmosphere. So if it is giving good result, industry can be using that method also. So there is no harm, but to allow them to use it. It depends upon how much of this dust cake is removed and how effectively it is working. But I'll have to look into that part because I have not come across yet theoretically.
Okay, sir. Thank you.
Okay, Dr. Gaurav.
Hello, sir.
Uh,
Sir, regarding a scrubber, how to maintain L over G ratio, like in the old industry, something or
again,
small scale industry.
again, I say my limitation so far as the design aspect is concerned. I have given you
Okay.
one source of book that you can use it because
It's a
in my
mass transfer, chemical
mm,
engineering
because chemical
problem.
engineers are more I would say Dr.
L by
Rotliwala
G
is the
ratio,
best.
that is of related to mass transfer operation, absorption. Uh, it is part of the syllabus.
Yes, yes.
Okay,
So
sir.
in
L
our
by G
MTech,
ratio.
we don't cover that the design part because chemical engineers are the best still.
Right,
Thank
Okay,
you,
sir.
absolutely.
Dr. Rotliwala, for helping me out.
Yes.
But anyways, that was good interaction from your side.
Sir, can we share your email address to the participants
Yeah,
because
please,
few of them
you
are
can.
still having the question, but we are running out of time.
Sure, you can do that. I'll try to respond to as many as I can.
Yeah. Thank you so much, sir. Thank you so much
Okay.
for your valuable time and presence.
And thanks for giving me this opportunity once again. Thank
Thank
you.
you. Thank
The
you so
pleasure
much,
is
sir.
all ours, sir. Thank you.
Thank you. Thank you. So I'll
Bye,
be
sir.
leaving the session now. Okay.
Okay, sir.
Thank
Okay. Yeah.
Bye.
So participants, we will be taking a 2-3 minutes bio